Major steps in coal mining. We will explain the process of fractional distillation of crude oil. We'll explain the process of cracking. We'll have an understanding of the factors that determine octane rating in fuels and recognize the consequences of the burning of fossil fuel on the environment. The key concepts we will look at: coal mining, crude oil, fractional distillation, cracking, and octane rating. We classify energy resources into two main types. The first one, renewable resources. These are constantly being produced on Earth, and examples are solar energy, wind energy, geothermal energy, and wave energy, biomass energy. And an example is shown here where we have solar panels using sunlight to generate solar energy. These are renewable resources. The non-renewable resources produced millions of years ago, and they cannot be replaced. They are used up. And these examples are nuclear fuels, for example uranium, and fossil fuels, coal, and also natural gas. These are non-renewable resources. Firstly, let's look at fossil fuels. Now, coal as a fossil fuel is the compressed remains of plants and animals and approximately 300 million years old. Coal reserves are formed from many of old remains of vegetation. The oil and gas is a compressed remains of oceanic microplankton, and that's approximately 100 million years old. So the fossil fuels are hydrocarbons made up of hydrogen and carbon, which combust in oxygen and generate a large amount of energy. So the equation can be shown as follows. The hydrocarbon plus oxygen will generate carbon dioxide, water, and a large amount of energy. The reverse reaction takes place during photosynthesis. This exact reaction in reverse is what occurs in photosynthesis, and we get carbon dioxide and water plus a large amount of sunlight energy would generate your glucose, which is your hydrocarbon, and oxygen. Examining coal in South Africa, we find South Africa is one of the world's top 5 coal producers. It is one of the world's top 3 coal exporters, and Eskom and Sasol produce most of the coal for the domestic market in South Africa. Coal fields are mainly found in Mpumalanga, which is 83% of South Africa's coal fields, also the Free State, Northern KwaZulu-Natal, and Northwest provinces. 28% of our production of coal is exported. Let us examine coal mining. First of all, coal, the black solid, occurs between layers of rock in horizontal layers or seams. Coal may occur on the surface or deeper underground. Remember, the shape of the layers of the earth underwent many changes over many millions of years, creating folds and twists in the seams. The result of this is that some coal may be found on the surface and some may be found deeper underground. The result is that you get open cast mines which are used to collect the coal from the surface of the earth, whereas deeper underground coal is mined by shafts, mine shafts that are sunk deep down, and horizontal tunnels are then dug into the coal. And we can see in longwall mining, heavy equipment is used to remove the coal, and heavy equipment is used to support the roof, because the roof could eventually collapse if there's not strong support system put into the mine. The board and pillar method, there's a crisscross pattern of tunnels, and large areas are left of the coal pillars to support the roof, and the roof is secured with some long steel bolts. After the board and pillar method, this crisscross of tunnels, later the pillars can be partially removed and pillar extraction takes place to extract the coal from the pillars, and this optimizes coal extraction. Most of Eskom's coal-fired power stations are built very close to the mines from which the coal is supplied. Let's have a look at a coal-fired power station and the structure. First of all, the coal is pulverized or crushed to a very fine powder. This is then supplied into a boiler furnace. The powder and hot air is blown into a boiler furnace. A large container and the powder, the coal powder and hot air is pumped into this furnace. The coal combusts and generates heat and energy. Remember, we said hydrocarbon plus oxygen, when it combusts, releases a large amount of energy. And since there is condensed water in the boiler walls, this is pumped around the furnace, and we can see now a high temperature is being generated by this heat of 1200 degrees Celsius, and so the water is turned into high pressure steam. And this water or steam, now it's been at this high temperature, comes out and is fed to turbines, which is then fed to a generator, and this in turn turns the turbines and the generators, this high pressure steam, and we get, in other words, this steam generates mechanical energy, which is then converted into electrical energy, and electricity is generated by electromagnetic induction, and the steam is then cooled and pumped back into the furnace. So this is the structure of a coal-fired power station. Most of South Africa's electricity is produced in these coal-fired power stations. At present, burning coal is a most cost-effective way of generating electricity. However, we need to look at alternative energy sources using renewable resources such as solar energy, wind energy, wave energy, and other forms of renewable resource utilization. Most of South Africa's electricity is produced in coal-fired power stations. Here's a diagram illustrating the process. The coal comes into the boiler furnace. Remember, hot air is also pumped into the system. Because of the combustion, high temperatures are generated, 1200 degrees Celsius, and since water is pumped into the system, it is converted into steam, and the steam is moved to where the turbines are. This turns the turbines, which in turn turns the generator, and electricity is generated. So mechanical energy is converted into electrical energy. The transmission lines go through transformers and eventually supply electricity to your households and industries. The water, the steam, is cooled and converts back into water and is circulated through the system again. So we have a condenser cooling water system, and this allows the water to be circulated throughout the system. The disadvantage of producing electricity from coal is that it has more waste products than any other energy source. And since coal is not pure, it contains a wide range of other compounds, including sulfur and nitrogen, and therefore we get sulfur and nitrogen oxides formed, we get organic compounds, radioactive compounds, and ash. And also, from the process during combustion, carbon dioxide and water are released. These waste products, all these, contribute to global warming and can cause serious environmental and health hazards. Crude oil for South Africa. Crude oil is a viscous, dark brown liquid that moves through underground porous rock. To extract the oil, we need to drill holes into this rock and so that the oil can be pumped out. Now, South Africa has no crude oil reserves as such, and South Africa imports most of its oil from the Middle East and Nigeria, the rest from Kuwait, Russia, and Angola. The chemicals in oil must be separated, and this is usually by a process called fractional distillation for the chemicals to become useful. And South Africa has 4 oil refineries. We have Caltex, or Chevron, Milnerton in Cape Town, Sapref, which is Shell and BP, and Engen in Durban, and Natref at Sasolburg. When we consider crude oil or black gold, it's a mixture of many chemicals: alkanes, alkenes, cycloalkanes, and aromatic compounds. To separate them into different components and chemicals, we use a process called fractional distillation. So fractional distillation is a separation of crude oil into the separate chemicals by using their boiling points. It uses a fractionating tower, which is approximately 100 meters tall, and which is hottest at the bottom and coldest at the top. The crude oil is fed in at the bottom of the tower, and most of the oil evaporates and the vapors cool down as they rise. When the condensation point of a chemical is reached, it condenses, it cools and condenses in a tray, and then that fraction is collected, and hence this name called fractional distillation. We're now going to examine this fractional distillation a little bit further. Examining fractional distillation, we look at the fractionating column, which is up to 100 meters in height, and as we go up the column, the temperature decreases. You have decreasing boiling points, and as you can see, these will be stainless steel trays, and the fractions are collected at different boiling points. Now remember, the density and boiling point is decreasing, and therefore the carbon chain length will also be decreasing. Your shorter chains are up at the top and your longer chains down at the bottom. We can see here the crude oil is pumped in at the bottom of the column, and a part which is not evaporated at all is collected, called the bitumen, which is a substance that's mixed with crushed stone and is used in tarring surfaces of roads. So we'll get the tarmac that you surface your road, and also used in roofing. This fraction, diesel oil, lubricating oil, and fuel oil, this fraction, these three, are around about 260 to 350, and these are about a carbon 14 to carbon 18 chain. Then we look at kerosene, which is a jet engine fuel. That has a carbon chain length of C11 to C13 and a boiling point of approximately 150 to 260. Looking at gasoline and naphtha, these two fractions, the petrol in our cars, octane, is in this fraction, and this is carbon 5 to carbon 10 and a boiling point of about 30 to 135. These are petrol and organic solvents such as naphtha, which is used for making chemicals, naphtha. At the top here we have refinery gas, which is used in cooking fuel, cooking gas, and that's C1 to C4 and a boiling point range of minus 161 to 20. We now present a summary of the fractions in the fractional distillation process. Starting at the top of the column, the natural gas, which is C1 to C4 carbon chain, and the boiling point range is minus 161 to 20 degrees Celsius. The use of this is in cooking gases. The gasolina-naphtha fraction, C5 to C10 chain length, and a boiling point range of 30 to 135. This is petrol and the organic solvents. The kerosene, which is C13 and C11 to 13, and that's 150 to 260 degrees Celsius. That's used in jet engines and in illuminating paraffin. Gas oil and diesel oils are C14 to C18 with a boiling point 260 to 350, and that's diesel fuel and catalytic cracking. The oil and the residue at the bottom of the column greater than C18, a boiling point range of 300 to 370, and you get lubricating oils, waxes, and bitumen. Catalytic cracking. Catalytic cracking is when the large molecules are broken down to produce smaller molecules, smaller carbon chains. So the larger carbon chains are broken down into smaller carbon chains, for example in petrol and naphtha. A fraction of high molecular mass alkanes is mixed with a catalyst, either a cobalt or platinum catalyst, at 500 degrees Celsius, and we'll see that smaller alkanes and alkenes form, which are separated by fractional distillation. An example of this process can be seen in decane, which is a 10 carbon long chain, dec 10, so 10 carbon chain, a much longer chain, and it's broken into two smaller chains. Ethene, which is an alkene because it has a double bond, which is 2 carbons, and octane, which is 8 carbon chain. Remember that what's on this side of the equation should balance with what's on the left hand side of the equation. Reactants equals products, and therefore a total of 10 carbons on this side and 10 carbons on the left hand side. So make sure the equations are balanced when you're breaking down your large carbon chains in catalytic cracking to smaller carbon chains. Looking at the octane rating, when you fill up with petrol, octane is an alkane with 8 carbons. Now if we look at the efficiency of the fuel, we look at the ignition, how quickly it ignites, and this determines the effectiveness of the fuel, and we call this the octane rating. If it ignites too quickly, the engine won't run smoothly and it'll make a sound called a knocking sound in the engine. And if the ignition of the fuel is too difficult, then the engine won't start at all. So the structure of the hydrocarbon is important because it affects the knocking and the efficiency of the engine running. So branched alkanes and cycloalkanes burn more evenly than the straight chain alkanes, and alkenes burn even more evenly than the alkanes. In octane rating, you will notice that the petrol pumps display a number called the octane number or the anti-knock rating. So next time you look at a petrol pump, you'll see 91, 93 or 95. This is a rating on its efficiency, octane rating. The octane number compares petrol to isooctane, which is a good anti-knocking fuel, and heptane, which is a very poor one. Remember, heptane is a straight alkane. A high quality petrol has many branched hydrocarbons. So something like isooctane, which has many branches, has a higher octane rating. If you look here, heptane is a 0 octane number, pentane 25, and butane 91. Isooctane, the branched alkane, has an octane number of 100, and toluene 112. So the higher, the more branches, the higher the octane number, and the straighter the chain and the shorter, the lower the octane number. Additives to petrol and pollution. Tetraethyl lead is added to boost the anti-knocking of the petrol, but lead, when released to the atmosphere, is poisonous. So during the combustion of the petrol, this lead is then released, and this is a poisonous component and pollutes our atmosphere. So we now have the LRPs, which are the lead replacement petrols, which are environmentally friendly. They have an additive added, such as an oxygenate TAME. This is a tertiary amyl methyl ether, and this component then takes out the lead, which is a poisonous substance. So we've come to the end of this DVD on energy resources. We suggest you look at the additional challenges in the Study Master Grade 11 book, and the Activity 5, which is investigating coal, on page 335, and Activity 6, investigating oil refining, and that's page 339 and 340. Enjoy the section on chemical systems, and remember to study hard.